Imagine a star that has been moving silently through our sky for more than a century, invisible to the naked eye, but traveling faster than any other star we can observe. Barnard's star, a small and faint red dwarf, is located a short distance away. For decades, astronomers have wondered if it hides any secret, and now, thanks to a recent discovery, they have confirmed that it does. Orbiting around this nearby star is a planet, a rocky world. How has it remained hidden from our eyes for more than a century? What does this mean for our search for life, and how might it affect the future of exoplanet research? The implications could be far-reaching. Join us as we discover a planet, a rocky world. How has this world been able to remain hidden from our eyes for over a century? What does this mean for our search for life, and how might it affect the future of exoplanet research? The implications could be far-reaching. Join us in this debate. Barnard's star is about 6 light-years from Earth, making it one of our closest neighbors in the galaxy, second only to the Alpha Centauri system. Unlike Alpha Centauri, a complex multiple stellar system, Barnard's star is unique and belongs to the category of red dwarfs, one of the most common types of stars in our galaxy. Despite their abundance, red dwarfs are difficult to observe directly due to their relatively low brightness. For example, the Barnard star only has 16% of the mass of the Sun and less than 0.004% of its luminosity, which makes it invisible to the naked eye. Naturally, the physical characteristics of Barnard's star distinguish it from its larger and hotter counterparts, with a surface temperature of about 5,400 degrees Fahrenheit compared to the 9,900 degrees Fahrenheit observed on the surface of the Sun. The Barnard star mainly emits infrared radiation, which means that any potential planet orbiting around it would have to be much closer to the star to receive the same amount of energy that the Earth receives from the Sun. One of the most interesting characteristics of Barnard's star is its unusual trajectory through the sky, with a proper motion of over 10 arc-seconds per year, giving it the title of fastest star in relation to the solar system. This movement results from its proximity and speed when traveling through the galaxy. Barnard's star moves at about 56 meters per second relative to our Sun. For astronomers, this rapid speed has been one of the main reasons why the star has been the object of close observation for more than a century. Its trajectory is so well mapped that astronomers can accurately predict its future movements. The star will continue to approach the solar system, reaching a distance of 375 light-years in about 10,000 years. Music. The story of Barnard's star began in 1916, when the American astronomer Edward Emerson Barnard first observed its peculiar movement. This astronomer measured the displacement of the celestial body with respect to the background of distant stars and realized that the object was moving faster than any other observed at the time. This discovery was revolutionary, since it pointed to the presence of relatively nearby stars moving at significant speeds. For decades, Barnard's star remained a primary target for observation, as its large proper motion allowed astronomers to study it in greater detail than most other stars. The first attempts to find planets around Barnard's star began in the 1960s, driven by its status as one of the closest stars to Earth. The first searches focused on detecting large gas giant planets, such as Jupiter or Saturn. However, the methods available at that time, in particular astrometry, were far from perfect. Astrometry consists of measuring small changes in a star's position caused by the gravitational attraction of the planets that orbit it. The challenge was to observe the oscillation of the star caused by the gravitational attraction of an invisible planet. But since the technology was still in an early stage, these measurements were prone to significant errors. Despite these limitations, in the 1960s and 1970s, astronomers such as Peter Van Camp claimed to have detected planets around Barnard's star using astrometric methods. Van Camp's team believed they had discovered a gas giant with a mass several times greater than that of Jupiter. This idea generated great enthusiasm, as it would have provided information on the formation of planets around red dwarfs, which are believed to be less conducive to hosting large planets. However, subsequent investigations ruled out these findings, and, As observation techniques improved, it became clear that the initial claims were based on data that was too inaccurate. The oscillation detected in the star's movement was not caused by a planet, but most likely by an instrument error or other source of error. In the 1980s, the idea of a massive planet orbiting Barnard's star was largely discredited, and astronomers had to reconsider their methods during the following decades. Astronomers developed more sophisticated tools, such as the radial velocity method, which allowed them to indirectly detect planets by observing changes in the light spectrum of stars. This method, which measures the movement of the star approaching or receding from the Earth, proved to be much more reliable. In the 1990s, these methods replaced astrometry as the main tool for the search for planets and stellar systems. However, the absence of planets around Barnard's star continued to baffle scientific minds, especially since other red dwarfs, such as Proxima Centauri, had been discovered to host planets, including some potentially habitable. Barnard's star, for its part, seemed to defy expectations. At the end of the 2010s, there was a great advance when technological advances, in particular the development of more sensitive spectrographs, allowed astronomers to observe the star with new eyes. In 2018, researchers announced again that they had detected a super-Earth orbiting Barnard's star, which rekindled interest in the system. This discovery was made using a combination of radial velocity data and other advanced techniques, confirming that, although there were no gas giants, small rocky planets could exist. The planet is believed to be slightly larger and to have a greater mass than Earth. This method tracks the star's oscillation by observing subtle changes in its light spectrum, in particular the red and blue shift of the star as it approaches and recedes from the Earth. The initial data suggested the presence of a planet orbiting at a distance of approximately 4 astronomical units from the star. However, in 2021, more detailed analysis revealed that the detected signal did not come from a planet, but was caused by the star itself. The internal variability of its activity caused color changes mimicking a planet's presence. In essence, what was interpreted as a planetary signal was actually the result of the behavior of a variable star. In 2020, the Super-Earth 22 did not exist, which was another false start in the search for planets around the star Barnard. However, it was in October 2024 when a turning point occurred in the investigation of nearby stellar systems. After decades of searching and refining techniques, astronomers finally confirmed the existence of a planet in orbit around the star Barnard, called Barnard B. Unlike speculative attempts of the past, this discovery is based on modern and high-precision observation instruments that provide reliable information about the existence and characteristics of the planet. The key to this advance was the measurements made with some of the most accurate spectrographs available today. The Espresso instrument of the Southern European Observatory Espresso of the Southern European Observatory and the HARP spectrograph. These tools allowed scientists to detect faint oscillations in the star's movement, which would have gone unnoticed with older methods. What makes this discovery especially significant is the extraordinary precision of these instruments. Barnard B is relatively small, approximately 37% of the mass of the Earth, but its presence was confirmed by the subtle impact it had on its host star. Unlike previous attempts, which were thwarted by technological limitations or stellar activity, this discovery is supported by a wealth of carefully analyzed and verified data by independent teams around the world. Barnard B has an incredibly short orbital period of only 3 days, which means that the planet is much closer to its star than Mercury is to the Sun, with an orbit at a distance of only 0.004 astronomical units. Such proximity results in extreme conditions on the planet's surface. The gravitational force of the star creates tidal forces that could cause significant internal friction and an increase in temperature in the core of the planet, combined with the radiation from the star, give rise to very harsh conditions in Barnard B. Given its close orbit and the fact that Barnard's star is a red dwarf, the planet is bombarded by intense stellar radiation and receives a large dose of energy that, according to estimates, raises the surface temperature to about 260 degrees Fahrenheit. This scorching heat makes the planet unsuitable for life as we know it. Water, if it ever existed, could not remain liquid and atmospheric conditions would likely be hostile. Despite the harsh surface temperatures, the discovery of Bernard B opens new doors to studying the nature of planets orbiting red dwarfs. Its small size and extreme orbit suggest it could belong to a broader category of exoplanets, more common than previously thought. The fact that Bernard B is a rocky planet rather than a gas giant supports the theory that small rocky worlds could be widespread around red dwarfs. Although ruled out in the case of Bernard B, the question of habitability remains intriguing in the context of red dwarfs. Although Bernard B is too close to Whittar to harbor liquid water, future studies could focus on searching for planets located further away within the system that could orbit within the habitable zone, a range in which temperatures are optimal for liquid water and planets with conditions more favorable to life are more likely to exist. At the same time, the discovery of Bernard B suggests that smaller, more distant worlds may exist in the system, waiting to be discovered. The potential for life on similar planets is further reduced by frequent stellar flares. Although Bernard stars are less volatile than other red dwarfs, they still experience bursts of ultraviolet radiation that could gradually strip a planet of its atmosphere. Planet's atmosphere. This phenomenon has already been observed in systems such as Proxima and Tor, where eruptions have made life less likely on nearby planets despite promising conditions. In the case of Bernard B, this means that, although it once had an atmosphere or water on the surface, it likely lost them long ago due to stellar activity. Red dwarfs, also known as M-type stars, are among the most common types of stars in the Milky Way, accounting for about 70% of all stars in the galaxy. Their widespread presence makes them a key target in the search for exoplanets, especially since they tend to be relatively stable and long-lived, which in theory provide an extended window for the formation and evolution of planets. However, these red dwarfs offer exciting possibilities. The study of these stars and the search for possible exoplanets has revealed exciting opportunities and important challenges. The stability and longevity of red dwarfs are the main reason astronomers focus so much on them in exoplanet research. They burn their fuel much more slowly than larger stars, like the Sun, meaning their lifespan can span tens of billions of years. This prolonged lifespan provides more time for planets to form and, potentially, for life to evolve if conditions are right. In recent years, red dwarfs have gained attention thanks to discoveries such as the TRAPPIST system, which houses 7 Earth-like planets, 3 in the habitable zone. The discovery of systems like this has raised hopes that these stars may harbor planets with Earth-like conditions, possibly even liquid water. However, despite their promise, red dwarfs are also known for their unpredictability and potential hostility to life. The main problem is their tendency to produce powerful eruptions. These stellar flares, which can release bursts of ultraviolet and X-ray radiation, are much more frequent and intense than those of larger stars like the Sun. For planets orbiting close to these stars, which is necessary for them to be within the habitable zone, the consequences of these eruptions can be devastating, as they can strip a planet, expose the surface to harmful radiation, and prevent the development of a stable environment capable of supporting life. Another important challenge is tidal locking. Many planets orbiting red dwarfs are so close to their stars that they become tidally locked, meaning one side of the planet always faces the star, while the other remains in constant darkness. This creates an extreme temperature difference between the two hemispheres, further complicating conditions on the surface. The side facing the star can reach scorching temperatures, while the dark side plunges into glacial cold, with only a narrow strip between the two that could offer tolerable conditions. However, despite these difficulties, the large number of red dwarfs in the galaxy and the frequency with which Earth-like planets are detected in their orbits keep them at the forefront of exoplanet research. If only a small percentage of planets could retain their atmosphere and avoid the worst effects of stellar flares, the potential number of habitable worlds could be infinite. However, the discovery of Bernard marks an important one in the study of planetary systems. It shows that, even in systems where previous searches were unsuccessful, new discoveries can be made with the right tools. As the second closest stellar system to our solar system, Barnard star is ideal for more detailed observations. The study of the star Barnard could serve as a basis for a broader investigation of exoplanets, potentially revealing how common rocky planets are around red dwarfs and contributing to the search for planets within the habitable zones of other stars. The next phase of the investigation will probably focus on determining the exact composition of Barnard B. As technology advances, instruments such as the James Webb Space Telescope and the latest generation of ground-based observatories will allow astronomers to examine if it has one and collect more data on the composition of its surface. These missions could reveal if the planet has any unusual geological characteristics or if it experienced different environmental conditions in the past that shaped its evolution. This discovery is part of a broader effort to map the planetary landscape of our cosmic neighborhood. As observation techniques improve, astronomers hope to find not just one, but potentially multiple planets orbiting the star Barnard. Although these worlds may not be habitable, they could provide crucial information on how planets form and evolve in red dwarf systems, which remain some of the most abundant and least known stars in the galaxy. Reality, we believe that we know what the ground we walk on is, the air we breathe, the world we see, but the more we delve, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that make up everything around us are 999% space. In addition, there is time, which is not a constant tick-tock in the background. Time can stretch, slow down, and even stop under the right conditions. So, how much of what we experience is real, and how much is just a construction of our mind? What if the reality we rely on is just the shadow of something deeper, stranger, and infinitely more complex? What was reality for the first human beings? The answer was simple. Reality was what they could see, hear, touch, and smell. The world around them was interpreted through their senses, which guided them in their day-to-day. The rustling of the leaves announced the arrival of a predator. The distant creaking of a branch indicated the presence of prey, and the feeling of heat from a bonfire drove away the cold of night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell. These senses were the tools with which they cognized their environment. But for them, reality was limited to what was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, danger was near. If a smell was smelled, food could be found. If something could not be smelled, it might not exist. Survival was an ongoing process of interpreting these senses, often in life-or-death situations. Recognizing the difference between the roar of a predator and the whisper of the wind could mean the difference between safety and death. The first human beings lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned. It was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. What is beyond the senses? What forces shaped the world over time? The limitations of direct perception gave way to imagination and conjecture. This curiosity gave rise to the birth of new ideas. Reality was no longer tied to the physical world. The first human beings began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control. Through mythology and beliefs, they created a broader reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thought. The journey of humanity, which began with a simple need to survive, has evolved into something much more complex. In one of the first philosophical explorations of reality, Plato presents the allegory of the cave. In this thought experiment, prisoners have been confined to a cave all their lives, seeing nothing but shadows projected on the wall in front of them. These shadows are all they know. They mistake these flickering figures for reality itself. For them, The shadows are the only truth they can perceive. But what would happen if they were freed from their chains and turn around? What do they see then? Plato's allegory suggests that human perception is often limited. What we perceive as reality may be just a shadow of a deeper, truer existence. The path towards the understanding of truth and reality, argued Plato, begins with the questioning of the world as we perceive it. Plato's allegory is not only a philosophical exercise, but also a profound commentary on the limits of human perception. We can think that we see the complete panorama, but often we are limited by the limits of our senses and experience. Reality can, therefore, extend far beyond what we can observe directly in the physical world. Our understanding of reality underwent a significant change with the discovery of space-time in the early 20th century. Albert Einstein destroyed the ancestral foundations of classical physics by demonstrating that space and time are not separate entities, as previously thought, but are intertwined in a single fabric of 4 dimensions, space-time. According to Einstein's general theory of relativity, massive objects deform this fabric, creating what we experience as gravity. The planets revolve around the sun, not because they are attracted by an invisible force, but because the sun deforms space-time, creating a curved trajectory for them. This revolutionary concept has completely changed our vision of reality on a cosmic scale. Time is also not absolute in Einstein's universe. Time can stretch or compress, depending on the speed at which an object moves or its proximity to a massive object. This idea, the dilation of time, means that time in itself is relative, which changes our perception of how reality unfolds. The scientific method has allowed us to unveil this reality for centuries. The classical mechanics developed by Newton gave us the tools to understand the movement of objects, predicting their trajectories with precision. But as we began to delve into the nature of the universe, discoveries, especially in quantum mechanics and the theory of relativity, showed us that reality works in ways that common sense had previously defined. The search for the basic components of reality began millennia ago. In the 5th century A.C., the Greek philosopher Democritus suggested that everything in the universe is composed of tiny, indivisible particles called atoms. These atoms, he said, are the fundamental basic components of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists like John Dalton began to provide empirical evidence that all matter was composed of atoms. These tiny particles, invisible to the naked eye, come together in various ways, forming everything from the air we breathe to the stars in the sky. For a long time, atoms were thought to be the most fundamental, indivisible units of the physical world. But as our understanding deepened, we discovered that the atom itself could be divided into even smaller particles. At the beginning of the 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, demonstrated that atoms were not indivisible after all. Classical physics taught us that the universe works like a precise machine with predictable cause and effect. But quantum mechanics has shown that reality at its core is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty prevail. As our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units of matter. Within these particles, scientists have discovered quarks, elementary particles that come together in certain combinations to form protons and neutrons. Alongside them are the particles called gluons, which are responsible for binding the quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. However, quarks are different from anything else in the world of physics. They cannot exist individually, only in combinations bound by a strong force. This force is so powerful that trying to separate the quarks results in more quarks being formed. It is a strange and complex system that continues to challenge our understanding of the fundamental structure of matter. Subatomic physics, especially the study of quarks and gluons, has expanded the limits of our knowledge, making it even more unknown. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain unanswered. How do these particles interact at the most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers is string theory. This revolutionary idea suggests that fundamental particles we observe, such as electrons and others, are not point particles but tiny, one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to redefining particles, but suggests that these strings exist not only in the three spatial dimensions and the temporal dimension that we know, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They are so rolled up that they remain hidden from view. If string theory is correct, then reality may be much more intricate than we ever imagined and extend to realms we have not observed yet. This brings us to the Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics, proposed by physicist Niels Bohr. This interpretation is based on the idea that quantum particles do not have certain properties until measured. Before observation, they exist only as probabilities. It is the act of measurement, interaction with a conscious observer, that gives rise to reality. In other words, until a particle is observed, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied by the Copenhagen interpretation. Some prefer the more radical many-worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time the wave function of a particle collapses, the universe splits into two. In one, the particle follows one path, and in another, it follows a different path. Instead of converging, the universe splits into two. In one universe, the particle follows one path, and in another, it follows a different path. Instead of converging on a single result, all possible results occur, but in different branched universes. These parallel worlds exist simultaneously, each representing a different version of reality. The many-worlds theory offers an alternative to the idea that observation leads to the collapse of reality. Instead, it argues that all possible realities exist, but we are only aware of the one we inhabit. This is an amazing concept that expands the imagination and makes us think that reality is far more complex than what we see daily. Whether we adhere to the Copenhagen interpretation, the many-worlds theory, or some other explanation, one thing is clear. At the quantum level, the rules of reality are not what they seem. However, despite its elegance, quantum field theory remains largely unproven. The theory operates at such small scales that modern technology cannot verify its predictions, even with all our advances in subatomic physics. There is still so much that we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, are still in conflict with each other, especially when it comes to explaining gravity at the smallest scales. While the standard model describes particles and forces, it does not account for dark matter, dark energy, and a complete explanation of gravity, suggesting that there is much more to reality than we can perceive or measure. Therefore, the question arises, where are you now? Not in the physical or locational sense, but in the sense of experience. Your consciousness is the lens through which reality is perceived, but what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain, or something more, a fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property arising from the complexity of neurological processes, in which billions of neurons work together to form complex networks that generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity. But this explanation does not fully solve the mystery. The hard problem of consciousness, as posed by philosopher David Chalmers, is how and why subjective experience, the sensation of consciousness, arises from purely physical processes? Why does a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? Thoughts. The gap between the physical functioning of the brain and the richness of conscious experience remains one of the most puzzling questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something far more fundamental. Some theories suggest that consciousness may be woven into the very fabric of reality, like space and time. This idea, known as panpsychism, asserts that consciousness is not limited to humans or animals, but is a basic property of all matter that permeates the universe to some extent. Therefore, if consciousness is fundamental, it could mean that the universe itself has consciousness to some degree. This shifts the question from how does the brain produce consciousness to how does consciousness manifest through matter. This, in turn, suggests that the distinction between mind and matter may be artificial, and that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this view, the complexity of the brain creates consciousness in the same way that water arises from individual molecules of hydrogen and oxygen. According to this view, consciousness depends completely on the physical structure of the brain. When the brain stops working, consciousness disappears. But this explanation still does not answer the fundamental enigma of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes, or is it something more, something that perhaps escapes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window to a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the grand scheme of existence, remains unknown. The more we learn about the brain and the universe, the clearer it becomes that reality may be far more complex than we currently understand. Perhaps someday discoveries will prove that consciousness is not just something that occurs within reality, but a fundamental key to understanding reality itself. There are countless untold stories in the universe, but a mystery veiled in the shadows of a distant sun stands out among many others. This discovery invites us to look beyond terrestrial limits and reflect on ancient possibilities. This is the story of Kepler-22b, a planet that not only wanders in the void, but occupies the optimal point, the habitable zone of its star. Here, in this delicate balance, all conditions exist for the magic of life to ignite, for water to flow freely, and the atmosphere to hold the secrets of existence. Discovered by the Kepler Space Telescope, Kepler-22b invites us to reflect on what worlds may exist beyond our own, to question our understanding of life and our place in the universe. It makes us dream of new horizons and distant shores where humanity could one day set foot. Today we will embark on a journey of discovery to unravel the mysteries of Kepler-22b and the countless worlds that await us beyond our reach in the unlimited vastness of space. In its search for Earth-like planets scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer charting a map of the unknown. At first, the Kepler mission was very clear: to observe the immensity of the Milky Way in search of the faint twinkling of stars dimmed by the passage of planets in their orbits. Equipped with the most sensitive photometers, the telescope patiently observed the light of more than 150,000 stars. Among them, a pattern emerged, the rhythmic fading of a particular star, very similar to our Sun. This was the first indication of Kepler-22b, a planet that moved carefully around its star and briefly eclipsed its light, as if playing a cosmic hide-and-seek. This discovery was a major event. The analytical capacity needed to examine huge data sets and select planetary transits from the cacophony of cosmic noise was immense. It was like detecting a slight difference in brightness caused by a moth flying in front of the beam of a lighthouse thousands of kilometers away. The transit method, Kepler's main tool, is a seemingly simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them briefly and casting a small shadow that causes a slight dimming of the star's light. It is this faint and fleeting shadow that astronomers are looking for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable decrease in its brightness. This decrease, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of light obscured tells us the size of the planet compared to its star. In addition, the regularity of these brightness variations reveals the orbital period of the planet, that is, the time it takes to complete an orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate the distance a planet is from its star, providing crucial information about the planet's environment and its likelihood of being habitable. This method also opens a window into the planet's atmosphere, since when the light of a star passes through the atmosphere of a planet during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the spectrum of the star, astronomers can determine the chemical composition of the atmosphere, finding traces of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler-22b was a defining moment in the search for Earth analogs, as it highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has further advanced the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow strip where conditions are perfect, where the hope of life as we know it endures in the darkness. This region, known as the habitable zone, is a cradle for potential life, a refuge where water can exist in a liquid state without boiling under the intense light of a star or freezing in the cold expanse of space. Imagine a world very similar to our Earth, located within this life-sustaining belt. Here, the heat of the star is neither too intense nor too faint, bathing the planet with a soft light. And here's where Kepler-22b orbits serenely in the habitable zone of its star, an ideal candidate in the search for Earth-like planets and, possibly, life beyond our solar system. Just as Earth thrives in its zone, Kepler-22b enjoys a similar privilege, orbiting at a distance where temperatures allow for the existence of lakes, rivers, and oceans. The presence of liquid water, universal solvent of many chemical compounds, is crucial, since it is in water that the chemistry of life develops. Water is the stage on which the drama of life unfolds, from the simplest bacteria to the most complex forms of flora and fauna. However, the presence of water in a liquid state is only one of the many conditions necessary to sustain life. What have we learned by analyzing this distant world, and is it so open to the theoretical presence of human beings on it? As we delve into the mysteries of Kepler-22b, we embark on a journey of discovery, reconstructing the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are understanding the fundamental nature of this distant planet, its size, its composition, and the air that surrounds it. These factors are what will help shed light on the presence of the building blocks that could make this distant world a cradle for life. So what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone of all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature could be favorable to maintain water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remain a crucial mystery. The atmosphere that envelopes the planet is the most important determinant of the environmental conditions that affect surface temperature and pressure, since the planet is in the habitable zone of its star. The theoretical presence of an atmosphere similar in composition to that of Earth, rich in nitrogen and containing the necessary amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have fueled life on our planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations to directly observe the atmospheres of exoplanets at such great distances. If the atmosphere of Kepler-22b tends to a denser composition dominated by carbon dioxide, like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that is too thin and free of greenhouse gases could turn Kepler-22b into an icy world where water would only exist in the form of ice and the surface would be exposed to harmful cosmic radiation. The planet's equilibrium temperature, estimated at a pleasant 22 degrees Celsius under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for life as we know it. However, if we went to the other extreme and created a greenhouse effect similar to that of Venus, the surface temperature could reach a scorching 86 degrees Celsius, which would likely prevent the existence of life as we know it. Things get even more complicated. The basic recipe for life goes beyond water in the appropriate atmosphere. Life, as we know, is intricately interwoven from a variety of chemical elements, among which carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur play a key role. Stars similar to the Sun, including Kepler-22, are G-type stars and usually have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a key role. However, during the formation of a planetary system, the distribution and concentration of materials in the protoplanetary disk around the star influence the composition of the planet's forming. The temperature gradients in this disk cause different materials to condense at varying distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, leading to the formation of distinct layers, such as the core, mantle, and crust, and by geological processes such as volcanic activity and plate tectonics. Thus, although direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the location of the planet in a habitable zone offer us the exciting possibility that the basic components that create the basis of the complex chemistry of life exist. While we wonder if the planet's atmosphere might contain a protective layer like ours, or if it is a dense, oppressive mantle that traps heat as a result of the greenhouse effect, all we know for sure is that the chemical composition of the planet is actually something we know for sure. The last of the four parameters necessary for life is an almost perfect agreement. The complexity of life must be fueled by energy, and Kepler-22b's presence in the habitable zone guarantees its constant supply from its host star. This energy, which fuels photosynthesis on Earth, could drive the fundamental biological processes necessary for life on that distant planet. The characteristics of a star slightly cooler and smaller than our Sun, but similar in many respects, provide a stable source of light and heat against the grandiose landscape of the cosmos. Kepler-22b stands out as a beacon of possibilities, a world where the basic ingredients for life as we know it may exist, but the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to seek the secrets of the universe and the potential for life beyond our solar system. The search for extraterrestrial life is a cornerstone of our celestial explorations, driving us to venture into the unknown with hope and scientific rigor as we turn our gaze to distant worlds like Kepler-22b. The next generation of telescopes and space missions is ready to pierce the cosmic veil and allow us to observe the atmospheres of these distant planets and discover their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built, with unprecedented sensitivity and resolution. The JWST is designed to observe the universe in the infrared, allowing it to detect the faint light from the first stars and galaxies and, more importantly, the atmospheric fingerprints of exoplanets. The JWST instrument suite carefully analyzes the light that passes through the atmospheres of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic molecular fingerprints essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, TESS, launched in 2018 and complementing the JWST, is to study the brightest stars near Earth in search of transiting exoplanets. Building on the legacy of the Kepler mission, TESS is expanding the search field and revealing many new worlds for study, including planets that share characteristics with Kepler-22b, which will be priority targets for detailed atmospheric analysis, opening up new opportunities to search for promising biosignatures. The Extremely Large Telescope, ELT, which when completed will be the world's largest optical telescope, will be another powerful tool in the search for extraterrestrial life. The ELT's colossal mirror, located on Cerro Armazones in the Atacama Desert, will collect light from distant exoplanets, allowing direct imaging and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of those distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large Optical/Infrared Observatory, LUVOIR, promise to further extend the limits of exoplanet research, equipped with advanced technology such as coronagraphs and star shades. AIDS. These observatories aim to obtain direct images of exoplanets by analyzing their light to reveal the molecular composition of their atmospheres in great detail. The search for extraterrestrial life, embodied in the exploration of these planets, continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It is a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts turn to the distant world of Kepler-22b, a planet in the habitable zone of its star. Here, in this hypothetical realm, we imagine the possibilities that such a world might hold. Could it be that the mountainous landscapes of this distant planet are home to a diversity of alien flora that thrives under the soft light of Kepler-22? Could it also be that its seas are teeming with life, with strange and extravagant forms adapted to the unique conditions of this distant world? What would be humanity's potential role in such a world? For now, it is difficult to imagine, but these dreams are sustained by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we look to the sky with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming Extremely Large Telescope, we continue to push the boundaries of our knowledge. Each discovery adds a piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's potential future among the stars reflects our deepest desires to explore, understand, and reconnect with the vast and wonderful cosmos that is our home. Music. Imagine a canvas of moments woven with threads of time and matter that stretches infinitely in all directions, capturing every choice, event, and heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what does science say? Will time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light but time itself. Did you know that astronauts aboard the International Space Station age more slowly than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let's travel through the corridors of time and explore the scientific paradoxes and limitless possibilities that one day could make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humanity was fascinated by the skies and passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating calendars and methods to measure time. In the modern era, this fascination is found in new canvas, cinema, and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated as if through the dimensions of space. Then came Back to the Future, a pop culture phenomenon that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the flux capacitor, and the charming eccentricity of Doc Brown? His charming eccentricity? But it is not only a Western phenomenon. The charm of time travel knows no cultural or linguistic borders, from Steins Gate in Japan to the Soviet Ivan Vasilievich. Back to the Future. The theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The charm of rewriting history, the emotion of the unknown, or the philosophical questions these journeys raise. It is a desire fueled by a mixture of nostalgia and expectation, a longing to relive endearing memories or launch into the promises of tomorrow. Now that we find ourselves on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we, should we, and what would happen if we were to travel in time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like mc²2 are not just keys to understanding the universe, but can they unlock the secrets of time travel? From the big screen to living room televisions, time travel has been represented in countless ways. But let's put fiction aside and delve into the science that could make time travel more than just a plot device. Let's meet space-time, the four-dimensional fabric of our universe, according to Einstein's relativity theory. Einstein's theory of relativity. This fabric can be bent and deformed by mass and energy, but can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different speeds depending on the speed of movement or the gravitational field. For example, astronauts on the International Space Station age slightly more slowly than people on Earth. Experiments with particles, accelerators, and atomic clocks have provided empirical evidence of time dilation. Particles traveling at speeds close to light have been observed to decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that, in theory, could shorten space and time. Although this is speculative, mathematics suggests that they are possible. The most prominent physicists and cosmologists have expressed their opinions on the matter, offering theories ranging from the plausible to the totally strange. Some even suggest that quantum mechanics, the science of the very small, could play a role in making time travel possible, and let's forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space, but also time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from reaching a consensus. Time travel raises questions that challenge the foundations of physics, from the nature of reality to the concept of causality. They say that time always moves forward and never backward. But what if we could jump forward, skipping years, decades, or even a century? The idea might not be as far-fetched as it seems. When it comes to slowing time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a small scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's now focus on the twin paradox, the famous thought experiment that takes time dilation to another level. Let's imagine two twins separated at birth. One travels through space at nearly the speed of light, while the other remains on Earth. Upon reuniting, the space twin will appear younger. Reaching speeds close to that of light would greatly enhance this effect, but such speeds are currently beyond the reach of our technology, not to mention that the energy requirements would be astronomical. Scientists and engineers are struggling with these problems and investigating propulsion technologies that could one day make it possible to travel at speeds close to light, to the speed of light. But even then, could the human body withstand such a journey? Let's imagine a future in which time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of freedom? Music from science fiction to scientific articles. Wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time could turn out to be the cosmic shortcuts we have dreamed of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points meet, then pricking them with a pencil in space-time. The wormhole would be that pencil creating a direct path between two distant points. This concept gained popularity in the scientific community thanks, in part, to Carl Sagan. While writing his novel Contact, he consulted physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving into the mathematics of wormholes with the general theory of relativity, which allows for their existence. The equations also assume that they collapse too quickly for anything to pass through them. In theory, by introducing some exotic matter, for example, one could counteract the gravitational forces that cause the wormhole to collapse, keeping it open long enough for something or someone to pass through it. The representation of wormholes in popular media often overlooks these complexities. They are usually represented as stable luminous vortices, but the reality, if they exist, may be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer models and indirect observations to understand their properties and potential uses. Let's imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present and the other in the future or the past. The implications for research and even for the prevention of global catastrophes are astonishing. Wormholes open the door to questions not only about where we could go, but also when. As we approach the possible discovery of these cosmic shortcuts, we must ask ourselves if we are prepared for the responsibility that comes with such power in the world of the very small, where particles are also waves and reality itself seems diffuse. The quantum world. Could this region of uncertainty contain the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Let's take the double-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that has been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics could offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if ghosts through walls. In the double-slit example, can a similar principle allow time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for current computers. The concept of quantum entanglement adds interest. Imagine two particles linked in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly amazing aspect of entanglement is that the state of one particle instantaneously affects its entangled partner, regardless of the distance that separates them, whether on the other side of the room or even on the other side of the galaxy. Change the spin of one, and the other changes instantaneously. Albert Einstein famously called it spooky action at a distance. At first, he did not like this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Did he like this idea because it seemed to violate the speed of light limit established by his theory of relativity? However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could a remote effect like this make a difference in instantaneous time travel? Although the intersection between quantum mechanics and time travel remains a matter of speculation, it is a hot topic in scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Let's imagine a future in which the principles of quantum superposition could explain multiple timelines or realities. What if we could exist in a superposition of the past and the present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Let's move on from the world of the microscopic scale to the grandly large. Black holes, mysterious titans of space whose gravity is so strong that not even light can escape them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves, CTCs. A closed time-like curve is a path in spacetime that repeats itself. In theory, an object, or even a person traveling along a CTC, could end up at an earlier point in time. The idea was proposed for the first time by the physicist Kurt Gödel in 1949. Gödel's solution to the Einstein field suggested rotating universes could contain loop trajectories in time. However, these solutions required certain conditions, like a universe full of rotating matter. Although the Gödel model is mostly considered physically implausible, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which CTCs can exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. The enormous gravitational and rotational forces can, in theory, twist spacetime into loops, creating CTCs, but there is a drawback. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped instead of point-shaped. This ring characteristic could potentially serve as a gateway to CTCs, but the powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is filled with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes where cause and effect are reversed. This has led some physicists to propose the chronology protection hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Will we be able to safely navigate such a treacherous region of space-time? And if we could, what will we find on the other side? Another universe or another time? In addition to black holes and closed time-like curves, there is another cosmic mystery that could open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe could be remnants of the Big Bang. Cosmic strings are believed to have formed in the early universe as it cooled after the hot, dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense and would have had tremendous gravitational force. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. J. Richard Gott and William Hiskok have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could, in theory, distort space-time enough to create a loop allowing travel to the past or the future. However, the existence of cosmic strings remains a matter of debate. Their detection would require astronomical observations on scales that currently exceed our capabilities. Furthermore, if they existed, harnessing their power for time travel would be a challenge. Let's go back to quantum entanglement now. We have already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be united in time? Some theories suggest entangled particles can be used to transmit information not only in space, but also in time. Let's imagine a future where quantum entanglement is used to create a quantum internet that allows instantaneous communication between eras. The intersection between cosmic strings and quantum entanglement is a frontier of theoretical physics, full of unanswered questions and unexplored avenues. Researchers are exploring how both phenomena could be connected and what this could mean for our understanding of time travel. Imagine a scenario where cosmic strings are manipulated at the quantum level through entanglement. This would represent a fusion of the very large and the very small, a meeting point between the cosmic and quantum scales that could revolutionize our concept of time travel. As we delve into the realm of time travel, we face many paradoxes and enigmas. These are not just intellectual exercises, but fundamental questions that can make time travel possible or impossible. First, there is the grandfather paradox. Imagine you go back in time and don't allow your grandparents to meet. If they never meet, one of your parents will never be born, and, therefore, neither will you. But if you were never born, how could you travel in time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest these paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confusing paradox is the so-called bootstrap paradox, which takes its name from the popular expression, pulling oneself up by the bootstraps. Imagine you go back in time to give Shakespeare a copy of your plays, which he then claims as his own. In that case, where did those works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox is the predestination paradox, which occurs when a time traveler's actions in the past lead to the same event he was trying to avoid. This raises questions about free will and determinism, and whether we can really change the course of history. The study of the paradoxes of time travel is not only a game for philosophers, but a serious area of research in physics and metaphysics. The resolution of these paradoxes could shed new light on time travel. As we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching real science, from cosmic strings to quantum entanglement, from rotating black holes to near-time curves. We explore the theories and possibilities that could one day make time travel a reality. Current investigations are paving the way for new experiments, technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we prepared for what we might find? Time waits for no one. But what if we could wait for time in the vast expanse of our solar system? Beyond the familiar glow of Neptune, rumors of an invisible presence have stirred astronomers for several years. This mysterious force, invisible but undeniable, stretches the very fabric of our cosmic neighborhood, deflecting the trajectories of distant objects with its grip. Here, in the shadowy depths of space, where the sun's heat barely reaches, lies a mystery that has baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence cannot be determined by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital movements. Could there be a wandering planet shrouded in the darkness of space that exerts its influence from afar, defying our understanding and testing the limits of what we know about our solar system? Join us as we gather the clues scattered within the confines of the solar system in search of a planet that has so far eluded our sight. At the dawn of our era, the confines of our solar system began revealing their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the limits of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly holding that title since its discovery in 1930. But as the Kuiper Belt revealed its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, which rivaled and even surpassed Pluto in size, unleashed a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union faced an unresolved situation. What defines a planet, exactly? The answer to this question led to a controversial decision that demoted Pluto to dwarf planet. This decision, met with both approval and opposition, has shaken the astronomical community and the public, redefining the way we conceive of the solar system. However, in this cosmic controversy, the seeds of a new mystery were sown. The peculiar orbits of some objects in the Kuiper Belt, including the then distant and newly discovered TNOs, hinted an invisible influence guiding these icy bodies from the shadows. Could it be that another planet hidden in the vastness of space had created the architecture of the outer solar system? This question ignited the imagination of astronomers such as Mike Brown and Konstantin Batygin, who set out to discover the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world that hides behind Neptune and whose presence is only detected by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery as we delve beyond the familiar boundaries of the inner solar system. Before us opens a realm of icy bodies and distant orbits, here in the cold, dark regions. Beyond Neptune lies an enigma that has captivated astronomers for years. The Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are the separated TNOs, trans-Neptunian objects, whose trajectories are free from the gravitational influence of Neptune, and the ETNOs, extreme trans-Neptunian objects, whose orbits are so eccentric that they seem tied to some invisible force. What could be the cause of this unusual behavior? The answer may lie in the gravitational anomalies permeating this distant region. These anomalies, subtle but profound, indicate the presence of a massive object whose gravitational attraction shapes the orbits of these distant objects. The separated TNOs, whose orbits appear unaffected by Neptune, point to a disturbance in the gravitational harmony of the outer solar system. Meanwhile, the ETNOs, with their extreme orbits, paint a panorama of cosmic interaction. Guided by a hidden force, the search to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. After carefully tracing the orbits of these mysterious objects, scientists began to reconstruct the possible location and characteristics of this invisible planet in the quiet balance of our solar system. Each planet plays its role revolving around the sun in a rhythm that has been repeated for centuries, but beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis. In 2014, astronomers Chad Trujillo and Scott Shepard observed an intriguing similarity between the orbits of Sedna, 2012 EP-113, and several other celestial bodies, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey to delve deeper into the mysteries of the outer solar system. They developed this hypothesis through careful analysis and computational modeling. Brown and Batygin gathered previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the peculiar dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was thought to be 10 times that of Earth, but subsequent research revealed it to be slightly lower, though still significant, at between 5 and 6 Earth masses. This review painted the image of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends well beyond its immediate environment. Its gravitational influence can explain the grouping of the orbits of the distant TNOs and the extreme trajectories of the ETNs, which weave a complex celestial panorama. The Planet 9 hypothesis unleashed a wave of scientific investigations, and astronomers from all over the world joined the search for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulties, a testament to both the immensity of the universe and the limitations of our current technological capabilities. Its distant, presumably enormous, elliptical orbit takes it to the confines of our system, a region where sunlight is almost unattainable, enveloping the planet in total darkness. This remoteness poses a serious problem, since the potential position of the planet can encompass vast portions of the sky, which requires exhaustive and focused searches that cover these celestial extensions and minute details. It is something akin to trying to find a needle in an astronomical haystack. In addition, due to its distance from the Sun, the surface temperature of the planet is extremely low, meaning that it emits minimal thermal radiation, which makes infrared detection even more difficult. The lack of emitted and reflected light is aggravated by the glow of distant stars and the countless cosmic objects that fill the sky, each competing for the attention of our telescopes. Among other difficulties, the nature of the search is complicated by the enormous orbital period of the planet, believed to be thousands of years, since it is imperceptibly slow from our terrestrial perspective. Even after a decade, the position of Planet 9 in space will only have changed slightly, making practically impossible any attempt to observe its movement in the short term. This chilling slowness of movement means that traditional methods of planet detection, by observing its transit or movement against the background of the stars, are not viable. However, in the relentless search, astronomers use a series of sophisticated techniques and instruments, from terrestrial telescopes equipped with advanced adaptive optics to space observatories that elude the musica. Therefore, in the search for Planet 9, astronomers have had to go beyond traditional observation methods, which has led to the development of several innovative approaches aimed at refining the location of the elusive planet. They use unique aspects of the external environment of the solar system and the possible celestial interactions that Planet 9 could have with other objects. One of the proposed approaches involves the possible moons that could orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes the release of internal heat within the moon, which could make it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid oceans under the surface and also causes intense volcanic activity on Io. This internal heating causes the moons to emit infrared radiation in a more perceptible way than Planet 9 itself, providing an indirect but promising path for its detection. Another innovative method consists of tracking the trajectories of interstellar asteroids that pass through our solar system. These high-speed objects from regions outside our solar system could be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational tugs it exerts on the bodies that pass through. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose trajectory through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft traversing the outer solar system can also provide valuable information. Like asteroids, when spacecraft travel great distances between planets, their trajectories are subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unexplained gravitational anomalies that could indicate the presence of Planet 9. This method requires accumulating enormous amounts of data over long periods, since the gravitational effects are incredibly subtle. However, the results can be very significant and will compensate for the time spent moving from direct observation to indirect detection through a planet. The influence of a planet on its environment may be the key to unraveling one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also led to many theories and speculations about the true nature of this elusive object. Among the most intriguing are the hypotheses that Planet 9 could be a primordial black hole or a dense cluster of dark matter, representing a radical change from the traditional planetary vision. The idea that Planet 9 could be a primordial black hole introduces an unexpected twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities can be the size of an asteroid, but possess the mass of a planet. The possibility that Planet 9 is one of these ancient and mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this, of course, does not completely contradict the impossibility of its detection, since, in theory, such an object would not be larger than a basketball. According to another theory, the planet could be a concentrated mass of dark matter, a form of matter that does not emit, absorb, or reflect light, and that represents a significant part of the total mass of the universe, but remains one of the greatest mysteries. It is believed that clusters of dark matter, theoretical groupings of dark matter, arose from density fluctuations in the early universe as it expanded and cooled. These gravitational fluctuations led to the formation of dark matter structures ranging from small clusters to enormous halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable by conventional telescopic techniques. The primordial black hole and dark matter cloud hypothesis emphasize the profound implications of the search for Planet 9, far beyond the discovery of a new member of the solar system, whether it is an ordinary planet, a primordial black hole, or a dark matter cloud. One way or another, we will find ourselves on the right side of events. The search for Planet 9 is a testament to human curiosity and the relentless pursuit of the unknown. A recent preprint of a research article by the same Mike Brown and Constantine Ban and their colleague Matthew J. Holman, entitled Pan-STARRS 1, In Search of Planet 9, dated February 1st, 2024, reflects the meticulous efforts that are being made to discover this enigmatic member of our solar system. The study used comprehensive data from the Pan-STARRS 1 survey, which, with its broad and deep coverage of the sky, provided a unique vantage point for the search, focusing on single-night transients and using a sophisticated orbit linking algorithm. The researchers examined billions of detected objects, a task akin to finding a single grain of sand on the entire North American coast. The methodological approach represents a significant advance that builds on the foundations established by previous studies, such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 study, the elusive ninth planet remained absent, and no characteristics matching the search parameters were found in the data. This result, although it did not lead to the discovery of a ninth planet, considerably reduced the search area, excluding 78% of the parameter space in which the planet could reside. The remaining 22%, with poor observational coverage, was inaccessible to current detection capabilities and represents the next frontier of space exploration. The journey doesn't end with the investigation of the PS1. Next is the launch of the Vera-C Observatory. It promises to usher in a new era of astronomical observation with capabilities that can accurately traverse the veil of mystery, including that surrounding Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the immensity of the universe and the small but significant place we hold in it. When we contemplate the celestial tapestry, what lies beyond the observable universe? Our understanding extends from the familiar glow of our solar system to the enigmatic dark spaces that defy all the truths we cherish, from the rudimentary lenses of Galileo, who first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies. Our tools for probing the cosmos have evolved dramatically, but each discovery only uncovers a layer of deeper mysteries that await. The intriguing presence of dark matter and dark energy suggests that much of the universe is made up of invisible substances and forces that dictate the rate at which galaxies rotate and the universe expands. But could there be more beyond our universe? The multiverse theory proposes a spectrum of possibilities in which different laws of physics might apply. Each discovery, from black holes that curve the fabric of space-time to gravitational waves that resonate throughout the cosmos, is a puzzle to understand the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the deepest mysteries that define our universe and, possibly, others. Are we prepared to redefine our understanding of the cosmos and accept the boundless realms of a multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humanity has been probing the depths of the universe, it has begun to encounter phenomena that our traditional understanding of physics cannot describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first emerged from the study of the rotation curves of galaxies, according to Newtonian mechanics. The stars on the outer edges of galaxies should rotate more slowly than in the center, like the planets in our solar system. However, observations have shown that this is simply not the case. Instead, the rotational speed of stars and galaxies remains constant, suggesting that there is an invisible mass that exerts an additional gravitational force. This matter, detectable only through its gravitational influence, forms the very skeleton of the universe. By turning our gaze away from the hidden mass within galaxies, we encounter an even more elusive component, dark energy. This mysterious force drives the accelerated expansion of the universe, a phenomenon first detected by the strange behavior of distant supernovas. Instead of slowing down, as would be expected from the gravitational pull of all the mass of the universe, its expansion is a phenomenon first detected by the strange behavior of distant supernovas. Instead of slowing down, as would be expected from the gravitational pull of all the mass of the universe, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama, born from the collapse of the cores of massive stars. These gravitational giants warp space-time to the point that not even light can escape. The first direct image of a black hole has revealed a stranger and more fantastic universe than we could have imagined, and, instead of providing new answers, has only added questions to the existing ones. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, tearing apart space-time, which we have only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, providing us with new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that has been our main window into the universe. By analyzing these waves, scientists can unravel the secrets of the masses of black holes, their rotations, and the details of their fusion, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the mechanisms of the cosmos and find possible cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown. Guided by our deep curiosity about the cosmos, the discovery of countless worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the suffocating surfaces of hot Jupiters to the potentially habitable conditions of super-Earths, becomes the starting point for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to observe the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not only for discovering new planets. It is about understanding the conditions that can sustain life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades exploring the silent expanse of space, listening for the faint whispers of civilizations that may exist on these distant worlds. The use of technologies spanning a vast electromagnetic spectrum underscores the enormity of our search and the tantalizing possibility that we are not alone in the heart of the galaxy. SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone in the heart of the galaxy. The theoretical basis of SETI is the Drake equation, formulated by astronomer Frank Drake in 1961. The equation offers a way to estimate the number of active and friendly extraterrestrial civilizations in the Milky Way. The equation takes into account factors such as the rate of star formation, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the probability of intelligent life. The equation highlights the large number of unknowns that exist in this search, from the fraction of habitable planets with life to technological civilizations. However, the search for the potential of life in space is only the beginning. The more we delve into the mysteries of the cosmos, the more our knowledge expands and the more questions arise. The constant change in our understanding of the cosmos lays the foundation for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain the mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what is truly possible. The theory of the multiverse opens an even wider range of possibilities that goes beyond our observable universe, to realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we accept the theory of the multiverse, the equation may be only one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. The concept of the multiverse expands the limits of our cosmic understanding towards new, unexplored territories. It suggests that our universe, however vast and complex it may be only one of a vast, perhaps infinite, number of universes that exist in parallel to ours. The seeds of the multiverse theory are found in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes that arise from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own cosmos. Cosmic inflation, a theory that describes the exponential expansion of the early universe, provides another basis for the multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its own universe, within a larger multiverse. These bubbles may have different properties and physical laws, dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic, but include several models, each with its own implications for our understanding of reality. Bubble universes emerge from a theory of cosmic inflation. Bubble universes are distinct regions within a larger space, each of which has undergone its own inflationary expansion. These universes may differ radically from ours, with different physical constants and laws. Quantum multiverses. Based on quantum mechanics, this interpretation states that each point of quantum decision generates a new parallel universe. Each conceivable result of any event generates its own universe, giving rise to an almost unimaginable variety of parallel stories and futures. Mathematical universes. This model posits the existence of all mathematically possible universes. If the physical laws as we understand them are mere mathematical structures, all structures that can be mathematically described exist in a tangible way, just like our universe. For example, let's look at the type of multiverse classified by the cosmologist and astrophysicist Max Tegmark. Level 1. The infinite universe. In the first level of the Tegmark model, the universe extends infinitely beyond the observable cosmos. At this level, it is assumed that our observable universe, 92 billion light-years in diameter, is only a small part in an increasingly vast cosmic landscape. Each structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar, if not identical, conditions. Level 2. The post-inflationary multiverse. The second level of the Max Tegmark multiverse model explores the realm in which individual universes arise from their own unique Big Bang events. This classification is based on the concept of chaotic inflation, which posits the existence of a cosmos in which our universe is only one of countless universes generated by inflationary bubbles. Chaotic inflation suggests that the rapid expansion of the universe, which we call the Big Bang, is not a unique event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It only stops locally, like bubbles that form, separate, and boil. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can differ from one bubble to another. These differences can give rise to universes radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies, while in another, different levels of electromagnetic forces could change the chemistry of life, if this is possible there. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If we extend this analogy to celestial mechanics, we can imagine that the planets could orbit much closer to their stars, and that these could be smaller and burn faster. If physical constants can vary so much, the conditions that led to the appearance of life on Earth are only one possibility in a vast cosmic lottery. Each universe can be a unique experiment to explore the possibilities of physical reality. Although the second-level multiverses differ fundamentally in their constants, they share a common link with their first-level counterparts, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what is possible, but also provides a basis for understanding the incredible variety of conditions in which universes can form. Level 3. The many-worlds interpretation of quantum mechanics, perhaps the most disruptive of the interpretations of reality. The third level introduces the concept of quantum mechanics into the multiverse theory. According to the many worlds interpretation, each possible outcome of each event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities, where each conceivable scenario occurs in its own universe. Imagine a simple, everyday decision, such as turning left or right on your way to work. In the interpretation of the many worlds, each choice gives rise to a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its own path of reality based on that single quantum decision. Another example is launching a coin in our daily experience. The coin falls on heads or tails. However, in the context of the interpretation of the many worlds, at the moment of the launch of the coin, the universe is divided in two, one in which the coin falls on heads, and another in which it falls on tails. Each outcome exists in its own universe, and the consequences of this simple event propagate outward, affecting others in each universe. However, this interpretation goes beyond the human scale and includes all quantum events in the universe. For example, the disintegration of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to divide into one in which the atom disintegrated and one in which it did not. Each of these universes would continue to evolve independently, accumulating its own unique history. The fascinating aspect of this level of the multiverse not only resides in its scientific implications, but also in the way in which it reflects the complexity of human decisions and the unpredictability inherent to life. Just as we can consider hypotheses about our past decisions, the interpretation of many worlds makes these alternatives a reality in countless parallel universes. Level 4, the ultimate set. The fourth level of the classification of the multiverse of Max Tart's represents the most radical and profound conception of all the possible universes. In this model, known as the mathematical universe hypothesis, reality is seen as a landscape of mathematical structures. Each structure defines an independent universe distinguished not only by its constants or physical laws, but also by potentially complete mathematical structures. According to the mathematical universe hypothesis, our physical world is not only described by mathematics, but is mathematics. This means that every conceivable mathematical structure exists as a physical reality somewhere in the multiverse. These universes can function based on mathematical rules entirely different from those we know and understand. To illustrate this profound concept, let's consider a simple object like an orange. Imagine you're holding an orange in your hand. It is familiar and tangible, but this orange is essentially a set of mathematical properties. The shape of the orange, the ideal sphere, is not only a physical shape, but a geometric expression that describes the contours and volume defining how the orange exists in space. Now think about the orange color that we perceive. This bright tone is not only a random characteristic, but is the result of the interaction of light with the molecules on the surface of the orange, which absorb and reflect light in specific wavelengths. Because the science of light, optics, is deeply mathematical, it is based on equations that describe how light behaves when it comes into contact with an object. Even the flavor of an orange, the combination of sweetness and acidity, is determined by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, which are essentially mathematical relationships determining how substances interact. Each and every aspect of an orange, from its growth to the sensations it evokes in us when we eat it, can be described using mathematics. In this way, this simple fruit becomes a small, tangible proof of a much greater truth. Our entire universe, from the smallest atom to the largest galaxy, can form part of a vast mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe describable by a coherent set of mathematical rules exists with as much certainty as ours. It implies that universes with radically different properties that defy our physical intuition are as real as ours. Let us consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter's formation and evolution. Or let's imagine a universe governed by a different type of geometry, in which the shortest path between 2 points is not a straight line, but another curve that radically changes the structure of the universe and the life it can harbor. Level 4 is connected with the other levels of the multiverse, providing the definitive framework, while levels 1 to 3 deal with the universes that differentiate in the initial conditions, the physical constants, or the quantum results. Level 4 encompasses all possible mathematical realities and offers a cosmos where the limits of what is possible are restricted only by the limits of mathematical imagination. The implications of multiverse theory go beyond physics and delve into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that, with all its complexity and beauty, our universe is only one of countless others, each with its own history, its own laws, and perhaps even its own forms of life in the scientific field. Multiverse theory raises profound questions about the nature of scientific research and testing, since, by definition, the other universes of the multiverse are beyond our observation. The theory treads a thin line between physics and metaphysics, forcing us to reflect on the principles of empirical science. Music, it is a small step for man, but a big one for us. As we contemplate the immensity of a universe and the possibility that countless worlds exist in the multiverse, our quest for space exploration continues to drive us forward. The next chapter of human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, toward Mars, and, finally, beyond our solar system, in collaboration with international and commercial partners. The NASA Artemis program marks a significant milestone in our efforts to explore the Moon. The Artemis program, named after Apollo's twin sister, aims to return humans to the Moon in the mid-2020s, with the ambitious goal of achieving a sustained human presence there by the decade's end. Unlike the Apollo missions, which were short visits, Artemis envisions a long-term presence of humans and robots on the Moon, using its resources and using it as a testing ground for the technologies necessary for deeper space exploration. The Artemis architecture includes Gateway, a lunar orbital outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of international cooperation in space. For its part, the red planet, Mars, has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for crewed missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, as well as a better understanding of the psychological and physiological effects of long-duration space travel. Crewed missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to look for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light spacecraft capable of traveling to our closest stellar neighbors, like the Alpha Centauri system. In theory, these spacecraft could accelerate to reach a significant fraction of the speed of light, which would allow them to reach Alpha Centauri in just over 2 decades after their launch. These missions could provide invaluable data on other star systems and potentially habitable exoplanets, thus paving the way for future interstellar explorations. Music, the journey to the Moon, to Mars, and, ultimately, to the stars is not just a series of missions, but the continuation of our fundamental quest to explore, understand, and connect with the universe around us. even as we delve into the next chapter of human space exploration, can expand the limits of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. What if the relentless advance of time, the ticking of seconds, the changing seasons, and the aging of our bodies are nothing more than a grand illusion? What if the past, the present, and the future, the pillars of our existence, do not really exist as we have believed for centuries? These questions have tormented philosophers, scientists, and everyday minds alike. Is time interwoven into the very fabric of reality, or is it a stubbornly persistent trick that our brains play on us? The more we delve into the mysteries of the cosmos, the more tempting a possibility arises. What if our entire reality were a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of the objects themselves, but creations of our brains, which interpret the wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on a universe that otherwise would be timeless. Let us consider the vibrant world of colors that surrounds us: a juicy red apple, a field of yellow sunflowers, the clear blue of a summer sky. At first glance, these colors may seem like fixed properties of the objects themselves, but the reality is much more complex. Colors do not exist independently in the world. They are born in our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of nuances that shape our visual experience. This process is simply about biology. People with different forms of color blindness perceive the world in different ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling that time flows incessantly forward, the division of our lives into past, present, and future, is simply a way of making sense of change within the universe. Perhaps, like color, time arises from the interaction between our consciousness and reality, which may be fundamentally timeless. The idea that time may be an illusion is not new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the structure of space-time, the question of time has constantly challenged our understanding. Today, we are going to delve into this enigma by exploring the scientific discoveries and philosophical puzzles that point to the possibility that time, as we experience it, is nothing more than a great cosmic deception. Time seems inescapable, permeating our lives, from the alarm clocks that shake us awake to the relentless countdown of birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute and unbreakable force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton, who imagined the universe as a vast stage with time as a universal clock that marked the passage of seconds at the same speed for everyone and everything. But then Albert Einstein arrived, and our understanding of time was shattered forever. Einstein's theory of relativity revealed that time is not a rigid constant, but a flexible participant in the cosmic dance that curves, stretches, and deforms depending on the speed at which you move and the strength of gravity. Imagine two identical clocks, one located on Earth and the other aboard a spacecraft traveling at a speed close to that of light. Interestingly, if you could compare them, the clock on the spacecraft would tick more slowly than the one on Earth. This mind-blowing concept is time dilation. The faster you travel through space, the slower you travel through time. This is not an abstract theory, but has real consequences. Imagine two twins separated at birth. One stays on Earth, and the other becomes an astronaut and spends years traveling at immense speeds. When they meet again, the twin who has traveled through space will have aged less than his brother who has stayed on Earth. Time will literally have passed more slowly for him due to the effects of time dilation. Time dilation may seem like science fiction, but a fact of our universe that engineers must take into account. GPS satellites that orbit high above the Earth and travel at significant speeds experience time slightly slower than we do on the surface. Their onboard clocks must be adjusted to stay synchronized and ensure that the maps on your phone remain accurate. Einstein's revolutionary theories changed our understanding of time. Suddenly, time was not a stable constant, but a dynamic actor in the cosmic drama. This scientific upheaval provoked a resurgence of philosophical debates about the very nature of time. If time dilation and curved space-time are real, how can we reconcile these concepts with our everyday experience of the constant flow of time? Let us explore some of the profound questions that arise at the intersection of physics and philosophy. A central debate focuses on the existence of the past and the future. Presentists argue that only the present moment has real existence. The past is a collection of memories, and the future a realm of possibilities. The eternalists adopt the opposite position and consider that all time, past, present, and future, is equally real and immutable, like a vast tapestry that unfolds. The growing block universe model attempts to build a bridge between these two visions. It postulates a fixed past, an open future that constantly branches into possibilities, and a present moment continuously expanding as our experience unfolds. These apparently abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan the future? If the future is already determined, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and decisions we make within it. Perhaps the most disturbing implication of the block universe is the challenge it poses to free will. If the future already exists, plotted like a vast network of paths, are our choices truly ours, or are we simply following a predetermined route? Is our sense of agency merely an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may be written already. Can the block universe truly coexist with free will? Some philosophers argue that even if our actions are fixed within a timeless extension, we still experience choosing and the consequences of those choices. Others suggest that true freedom could lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to move relentlessly forward, never backward? Physicists and philosophers confront different eras of time, each offering clues about the irreversible nature of events. The thermodynamic arrow is one of the best known and derived from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases within a closed system. This explains why eggs break, but never unbreak, and why ice melts but does not spontaneously refreeze. These irreversible processes give us the feeling that time moves in only one direction, but thermodynamics is not the whole story. Our mind creates a powerful psychological arrow of time. We vividly remember the past, but the future remains mysterious. Even the universe itself provides a cosmological arrow as it continues to expand outward from the Big Bang. These diverse arrows raise a puzzling question. Is the flow of time a fundamental property of the universe or a byproduct of how we experience the relentless unfolding of change? The strange realm of quantum mechanics disrupts our traditional understanding of time and space. Let us consider the phenomenon of entanglement, in which two particles are linked profoundly. Imagine a pair of gloves, one for the left hand and one for the right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open a box and find a glove for the right hand, you know instantly, faster than any signal could travel, that the other box contains the glove for the left hand. In the quantum realm, particles can become entangled similarly, with their properties inextricably linked. Measuring one instantly affects the other, even over great distances, seemingly faster than the speed of light allows. This paradox points to a universe in which connections could exist outside our usual understanding of linear time. Theories like loop quantum gravity go further, suggesting that space-time itself is not a uniform continuum, but is composed of tiny indivisible fragments, like threads of a cosmic tapestry. If this is true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of how these fundamental blocks interact. These mind-blowing theories force us to question the very nature of reality. Could it be that our experience of time, as a relentless flow, is an illusion born of our limited perspective within a universe that may operate according to principles escaping our current understanding? Perhaps the past, present, and future that we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the greatest enigmas of the universe. Is it a fundamental force interwoven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion, a convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes suggest that our experience of the flow of time is profoundly different from the true reality of the cosmos. If time exists as we perceive it, what does that mean for free will and our place in the great history of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws that escape our current understanding? We may never have definitive answers to these questions, but the mere act of asking them reveals the profound beauty and infinite mystery of existence. While the relentless advance of the clock and the passage of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continually defies our understanding. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed but holds secrets that could unlock some of the cosmos's most enduring mysteries, far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune. Tunnel. Uranus travels through the cold, dark corners of our solar system. It is a world that lives at a different rhythm, spinning on its side, a rarity that has puzzled astronomers and given rise to countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet found through a telescope, expanding the known limits of our solar system for centuries. This distant world was just a point of light in our telescopes, a ghostly blue ball, distant and remote, guarding its secrets. But now, with the arrival of the James Webb Space Telescope, a new chapter opens in the exploration of Uranus. The JWST, with its unprecedented vision, uncovers the layers of this ice giant and reveals a world of incredible beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In its quest to understand the universe, humanity has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, successor to the legendary Hubble Space Telescope, equipped with a set of advanced instruments and a mirror of more than 62 meters. The JWST is designed to observe the universe in a light invisible to the human eye, the infrared spectrum. This allows the telescope to pass through clouds of cosmic dust, discover distant galaxies, and study exoplanet atmospheres. The telescope's journey to space was a feat itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or journey to space was a feat itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or L2, 1 million kilometers from Earth. Here, in this stable orbit, The JWST can observe the universe with minimal interference from the Earth and Sun day. The JWST's capabilities are not limited to observing the early universe or galaxies. It also plays a key role in unraveling the mysteries of our solar system. Its powerful instruments, such as the NIRC near-infrared camera and the MIRI mid-infrared instrument, reveal new details about planets, moons, and other celestial bodies closer to us. Let's take Uranus as an example. In the past, our vision of this distant planet was limited to blurry images obtained with telescopes like Hubble. But now, thanks to the enhanced infrared capabilities of the JWST, we can see Uranus in new light. The telescope's sensitive instruments allow us to observe its weather patterns and even its mysterious rings with unprecedented clarity. By analyzing the light from Uranus, the JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases like methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations and reveal more details about our universe every day. Its latest triumph is a series of very recent images of Uranus, surpassing even the impressive observations made in April 2023. In early 2023, the JWST provided us with unprecedented views of Uranus, allowing us to observe the planet's atmospheric dynamics and ring system in a new light. However, the recent images go a step further. Not only are they clearer, but they reveal aspects of Uranus that were previously hidden or blurred, even in the April observations. Let's take the rings of Uranus as an example. The latest images show them more clearly, allowing us to observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of the JWST lies not only in its specific observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are especially striking. The bright white layers and dark bands near the poles, whose origin is still unclear, have shown remarkable changes. This continuous observation provides very valuable data for understanding the seasonal changes and long-term weather patterns on Uranus. In the set of planets in our solar system, Uranus stands out for a peculiar characteristic, an extraordinary axial tilt, different from that of any other planet. Uranus rotates practically on its side, with an inclination of approximately 98 degrees. This unique orientation has long intrigued astronomers and has triggered a search to understand its origin and its consequences. To understand the significance of this inclination, we must go back in time to the early days of our solar system. Probably, Uranus formed with a much less pronounced inclination. The prevailing theory suggests that a catastrophic event, perhaps a collision with an object the size of a planet, drastically changed its orientation. This colossal impact would have thrown Uranus to one side, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme inclination gives rise to extreme seasons different from those observed on other planets. The implications for planetary observation and research are enormous. The inclination of Uranus allows us to observe its rings and satellites from different perspectives, offering a vision into its composition and dynamics. For example, when the rings of Uranus are oriented towards Earth, they become almost invisible, revealing fainter dust bands and smaller satellites. Compare this to Earth, which is only a 235 degrees tilt. The extreme inclination of Uranus causes drastic changes in its weather patterns, which is a gold mine for scientists studying planetary climate. The inclination also affects the circulation of Uranus' atmosphere. Prolonged exposure to sunlight from the poles can lead to complex weather systems, as seen in recent images from the JWST. These systems are very different from those of other planets and constitute a unique laboratory for understanding atmospheric physics. Let's embark on a journey through Uranian year. Each season on Uranus lasts about 21 Earth years, as a result of its 84-year orbit around the Sun. This prolonged duration means that each hemisphere experiences long periods of daylight followed by equally long nights. As a result, the planet undergoes dramatic changes in its appearance and climate, as one pole of Uranus bathes in uninterrupted sunlight during the summers, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique conditions that lead to complex weather patterns and climate changes. The impact of these seasonal changes on the atmosphere of Uranus is profound. When the sun illuminates the planet's surface, it heats the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static but evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. In contrast, dark spots of storms that look like giant hurricanes roam the surface of the planet. In addition, the planet's seasonal phenomena not only affect the planet itself, but also its moons. A recent study of the moons of Uranus, or rather a particularly intriguing phenomenon, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranian system. The key to understanding these temporary atmospheres lies in the extreme inclination of the axis of Uranus and its effect on the orbits of the satellites. As these satellites orbit the planet, they experience drastic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer, exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to gas, without passing through the liquid phase. This sublimation creates thin, temporary atmospheres or exospheres that envelop the satellites. These exospheres are more pronounced when the moons are warmer. Recent research from the James Webb Space Telescope shows this phenomenon is more dynamic and complex than previously thought. The exospheres are heterogeneous, varying in composition and density depending on the moon's topography and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. The gases recondense on the surface and return to an icy state. This cycle of creation and disappearance of the atmosphere is a unique characteristic of the satellites of Uranus, which opens a window to the interaction between solar radiation and surface ice. The rings of Uranus, often eclipsed by Saturn's majestic rings, hold their own story of intrigue and cosmic dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. Unlike Saturn's wide and bright rings, the rings of Uranus are narrow, faint, and less extensive, extending up to 4 planetary radii. This includes elusive rings such as the Mu rings and the Nu rings. The study delves into the gravitational influence of Uranus' main satellites on these rings, a key factor in their formation and evolution. The significant influence of the 5 main satellites of Uranus, Miranda, Ariel, Yummel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranian system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of the rings of Uranus is attributed to a combination of processes including collisions, the breakup of satellites, and gas release from the main satellites. These dynamic processes affect the ring's material composition and are influenced by the constantly changing environment of the Uranian system. The stability of the rings is intrinsically linked to their dynamic interactions with Uranus satellites. The study examines how accretion processes occur within the Roche limit and how the dynamics of the shepherd moons play a crucial role in maintaining the rings. In addition, the rings offer a unique opportunity to understand the internal structure of Uranus through seismological studies. The model's results show how these satellites shape the ring system, affecting its structure and stability over time. The model predicts a significant loss of material within the ring system, mainly due to gravitational interaction with the satellites. The complex dance between the moons and the rings is a key aspect of the Uranian system. The dynamic exclusion zones created by the satellites and the influence of these zones on the distribution of the material of the rings are crucial to understanding the structure and evolution of the rings. The study also examines the role of interactions between satellites in the system's evolution, especially the past resonances between satellites, such as Ariel and Umbriel, and their impact on the orbits and geology of the satellites, especially Miranda. But the mysteries surrounding this planet do not end here. You have probably heard of the aurora borealis. Well, the latest discovery refers to the auroras of Uranus, which also has them. However, unlike those of Earth, its auroras occur in the infrared spectrum. Using the KK-2 telescope, astronomers observe an increase in trihydrogen cation emissions in the planet's atmosphere. This is a revolutionary discovery that sheds light on the unique magnetic field and atmospheric dynamics of Uranus. The magnetic field of Uranus, which deviates significantly from the planet's axis of rotation, creates a unique coupling between the magnetosphere, the ionosphere, and the thermosphere. The detection of these infrared auroras is crucial because it opens a new window into these processes which until now have been difficult to understand due to the lack of such detections on Uranus. The comparison of the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where H3+ emissions have a short life that smooths out the variability of UV emission, Uranus' brighter infrared emissions do not necessarily coincide with the other planets' brighter ultraviolet emissions. This unique aspect of them provides valuable information for the study of exoplanets, especially for the worlds of warm ice giants. The study delves into the unusual hot spots of Uranus observed near the latitudes of the UV aurora borealis. These points, analyzed in terms of temperature, column density, and total emission, suggest that the increase is not caused by temperature, but by increased ionization, probably due to polar auroral activity. The polar lights play an important role in the warming of the atmosphere, and, in Uranus, the increase in H3+ emissions associated with these auroras suggests their participation in atmospheric processes. By studying these unique phenomena, we gain a deeper understanding of similar processes in different planetary environments, which enriches our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas that invite further exploration. Recent research, including a new analysis of Voyager images, has revealed that the two planets actually have similar shades of blue-green, radically changing our ingrained beliefs. Uranus and Neptune share many common characteristics. They are approximately the same size, the same mass, and are surrounded by deep atmospheres of comparable materials. However, for a long time, it was thought that their appearance was quite different. This error has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer of their atmospheres. The need for a dedicated mission to Uranus has never been greater. A mission of this type would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar ice giants. The potential objectives of the mission range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the mission of the orbiter and the probe of Uranus has been elevated to the highest priority for the flagship mission of NASA within the Decennial Survey of Planetary Science 2023 to 2032. Future launch windows are available between 2030 and 2034. Key scientific objectives will include a detailed analysis of the unusual inclination of the axis of Uranus and its effect on the climate and weather patterns of the planet. The mission will also be able to study the intriguing phenomenon of infrared auroras and their role in warming the atmosphere, providing a comparative study with other planets. The study of Uranus and Neptune will also provide valuable information on planetary evolution and dynamics. Understanding why Uranus appears slightly wider, perhaps due to its more stagnant atmosphere that allows methane haze accumulation, can tell us a lot about the atmospheric processes of the ice giants. While we await a future mission to Uranus, we find ourselves on the threshold of discoveries that could redefine our understanding of the solar system. Exploring this distant ice giant will not only unravel its mysteries, but also expand our knowledge of planetology as a whole, shedding light on the complex image of our cosmic home in a universe dominated by massive ancient structures. There are places where something unexpected happens that defies the cosmic norm. New galaxies arise. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere in the confines of space, young galaxies continue to be born that shine with the energy of new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe is slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grandiose structures, the role of dark matter in all this, and the mysterious processes that allow some galaxies to defy time. The discovery and classification of galaxies was a milestone in our understanding of the universe in the early 20th century. Edwin Hubble's observations showed that the nebulae observed with telescopes were not only clouds of gas within our galaxy, but entire galaxies containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe replete with distant galaxies. Soon, galaxies were classified according to their shape: spirals, ellipticals, and irregular. These classifications helped astronomers to create a more organized vision of the cosmos, which led to a deeper study of the origin and evolution of these enormous structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were old, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were carried out, scientists expected to find a variety of galactic ages, including newly formed galaxies. However, instead of a universe full of young galaxies still in the process of formation, they discovered that most galaxies had already reached maturity. These findings challenged existing theories about cosmic evolution at that time, which raised questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that is still observed in the current universe. This paradox, the presence of ongoing star formation in predominantly old galaxies, posed a serious question to our understanding of the formation and evolution of galaxies. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies might not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, appear to have played a more important role in shaping its landscape than initially thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, which has led to a shortage of newly formed galaxies in the modern era. Determining the age of galaxies is a complex task that relies on various methods, most of which focus on the age of the stars that compose them. For example, astronomers have used various methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods consists of studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of the stars on their temperature. In particular, astronomers focus on the inflection point of the main sequence, the stage in which stars begin to leave the main sequence and become red giants. This point is very sensitive to age. The position of the inflection point in the HR diagram can provide an accurate estimate of the stellar population's age. Another important method is the study of globular clusters, dense groups of old stars that orbit around the periphery of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars, and since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about its formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis, analyzing light spectra, in particular absorption lines, to determine the relative proportions of different types of stars. The oldest galaxies are dominated by cooler red stars, while the younger galaxies have more hotter blue stars. The discovery that many galaxies, including the Milky Way, formed almost 13 billion years ago, shortly after the Big Bang, was a significant advance. 8 billion years, shortly after the Big Bang, was a significant advance in cosmology. The rapid collapse of primordial gas clouds under the influence of dark matter likely played a crucial role in these early formations. This process laid the foundations for the cosmic structures we see today. Therefore, the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were strongly linked. As the universe expanded and cooled, gravity began to attract matter towards the first structures, small clusters of matter known as protogalaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through electromagnetic forces and radiation, dark matter interacts primarily through gravity. Due to this, dark matter began to clump together before ordinary matter, forming the base on which the first galaxies finally formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to attract gas and dust, leading to the formation of the first stars and, eventually, the first gas galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They often had irregular shapes and lacked a distinctive structure like that of the Via Lactea, but over time, driven by the gravitational attraction of dark matter, these protogalaxies began to merge and interact. As the protogalaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and fusion is often known as the cosmic noon, an era of active formation and growth of stars through mergers at a much higher rate than we observe in the present universe. So, why are newly formed galaxies so rare in the modern universe? One of the key factors that contributed to this phenomenon was the very process of galaxy fusion in the early universe. When galaxies were smaller and more numerous, frequent interactions and collisions occurred between them. However, as the universe expanded and matured, these collisions became less frequent, leading to a smaller number of new galaxies. Another factor is the changing influence of dark matter halos in the early universe. The halos were smaller and more concentrated, which favored the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it difficult for gas to cool and condense into new formations. The large-scale structure of a universe, often referred to as the cosmic web, also plays an important role in this process. Galaxies are not randomly distributed, but are arranged along enormous threads of dark matter that stretch throughout the cosmos and connect galaxy clusters. Along these threads, gas flows into them, feeding the star formation process. However, in the current era, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of formation of new music. However, despite everything we have just said, there are exceptional cases that break this trend. One example of this is the regular dwarf galaxy IR known as ICE Wiki 18, located about 45 million light-years away. This galaxy stands out for having experienced a burst of relatively recent star formation. Unlike most galaxies, ICE Wiki 18 began its first major burst of star formation only about 500 million years ago, long after the period in which most galaxies in the universe had already fully formed. The slow evolution of IWI 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young, massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that ICE Wiki 18 did not experience the same evolutionary processes as most other galaxies. This late flowering may provide clues about the conditions that favor delayed star formation and raise the question of the role of environmental factors, such as interactions with nearby galaxies, in triggering or suppressing star formation. Another notable case is a galaxy with a rather complicated name, HSC J1-1631+4426, discovered thanks to observations made with a Subaru telescope located 430 million light-years away. This specimen is not only young, but also holds the record for the lowest oxygen content observed. The low oxygen content indicates that the galaxy is in the early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The small size of the galaxy, of about 8 million solar masses, comparable to a star cluster of 8 million solar masses, comparable to a star cluster of our Via Láctea, further underscores its youth. The fact that such a young and small specimen exists at such a late stage in the history of the universe is surprising, given that in the early universe the conditions for galaxy formation were much more favorable and that the expansion of the universe continues to accelerate, making it increasingly impossible for new galaxies to form. These findings are, therefore, quite extraordinary. At the same time, star formation is a continuous process that continues even in old galaxies, and star clusters like the Pleiades are clear evidence of this ongoing activity. The Pleiades, often called the Seven Sisters, are a young open star cluster located just 448 light-years from Earth. Despite the age of the Via Láctea, which exceeds 13 billion years, the Pleiades cluster is relatively new, having formed only about 100 million years ago. This indicates that, even in a galaxy as mature as ours, there are still regions of active star formation. The formation of star clusters, such as the Pleiades, usually occurs in regions of galaxies where there is a high concentration of gas and dust. These molecular clouds collapse under their own gravity, giving rise to new stars. In the case of the Pleiades, the stars in the cluster are still relatively young and hot, and emit a bright blue light that makes the cluster visible to the naked eye. These star clusters are not unique to our galaxy. In neighboring galaxies, such as the Great Magellanic Cloud, LMC, star formation is also taking place. The LMC, a companion galaxy to the Via Láctea, contains the oldest stars known, as well as regions where new ones are still forming. One of these ancient stars, LMC 119, discovered this year, is estimated by scientists to be about 13 billion years old. This discovery highlights the extraordinary longevity of some stars and suggests that we still do not fully understand the conditions for star formation. These star-forming regions are not only vestiges of the past, but a critical factor for the future evolution of galaxies, as the new stars that form contribute to the ongoing dynamic processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of the elements necessary for life. While star formation is an important factor in some regions of galaxies like the Via Láctea, another factor affecting the overall evolution of these galaxies is the presence of the dark matter halos mentioned above. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Via Láctea, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component that forms a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars and, consequently, new galaxies in the early universe. The halos of dark matter provide the gravitational wells necessary for the collapse of the gas and the formation of the first galaxies. However, over time, these halos grew larger and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current era. This dynamic creates a delicate balance in the cosmos, where dark matter both promotes and inhibits cosmic structure growth. According to scientists, the presence of these halos is one of the key reasons why today we see fewer new galaxies forming compared to the early universe, which marks a significant change in cosmic evolution. Understanding the shape and evolution of galaxies remains a key challenge of cosmology. Despite significant advances, debates continue about the fundamental processes that shape the universe. One key debate refers to the formation of structures in the cosmos, whether it occurs according to a descending or ascending approach. According to the descending model, large cosmic structures formed first and then divided into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the beginning of the universe, and the smaller structures were formed as these large structures disintegrated. In contrast, the ascending model suggests that small structures formed first, and the tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory aligns with the hierarchical nature observed in the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a basis for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of disks of ancient, massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. However, the search for an understanding of new galaxies continues to drive astronomical research. The JWST has already opened new windows to the distant universe, allowing astronomers to peer into an era when galaxies were forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxy formation, the current landscape presents a different panorama as the universe expands and dark energy accelerates this expansion. The conditions for galaxy formation are becoming increasingly rare. Future astronomical missions are prepared to further expand the current panorama, presents a different image as the universe expands and dark energy accelerates this expansion. The right conditions for galaxy formation are becoming increasingly rare. Future astronomical missions are prepared to further expand the limits of our knowledge. Instruments such as the Vera-C, Rubin Observatory, and the Euclid mission of the European Space Agency will soon carry out deep space studies that will likely reveal new galaxies that have eluded previous observations. These missions not only aim to discover new galaxies, but also to unravel the mysteries of dark matter, dark energy, and the universe's global structure. The history of the universe is far from complete as we continue to explore the cosmos. Discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe. Stay tuned for upcoming discoveries. What if the star closest to the Sun hides a world where human beings could one day live? In 2016, astronomers discovered Proxima Centauri b, a planet located only 4 light-years away. But reaching this neighbor is not just a dream. It is a challenge that modern science is beginning to address. Let's imagine a journey of more than 25 trillion miles. The technology we have today, such as the ion engines used in space missions, pales compared to what would be needed for such a trip. But hidden in the plans of a decade ago and in cutting-edge research are the keys to interstellar travel. However, distances are not the only obstacle we have to overcome today. We will talk about it and discover if humanity's next great leap can come true. The dream of interstellar travel has been part of the human imagination for centuries, but it was not until the 20th century that science began to catch up with science fiction. The journey begins with a momentous moment in 1961, when Yuri Gagarin became the first man to orbit Earth. This achievement paved the way for space exploration, demonstrating that human beings could survive and work beyond our planet. Then came the Apollo program, which included the historic moon landing of 1969. The steps of Neil Armstrong and Buzz Aldrin on the lunar surface were not only a victory for humanity, but also a demonstration of our ability to reach and explore other celestial bodies. In the 1970s, the Voyager missions provided invaluable data on the outer planets and the heliosphere. These probes, which are now in interstellar space, carry with them gold records with messages intended for any intelligent extraterrestrial life form that may find them. The voyages of Voyager 1 and Voyager 2 have allowed us to glimpse the immensity of space and the inspiring potential of travel beyond our solar system. But humanity does not stop. In recent years, the development of advanced propulsion systems has been crucial. The ion engines used in missions, such as NASA's Dawn spacecraft, allow for long-duration missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a method much more efficient than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized by the discovery of exoplanets, planets that orbit stars outside our solar system. The first confirmed exoplanet was discovered in 1992, when astronomers discovered two rocky planets orbiting a pulsar. This discovery broke previous notions and opened the doors to the search for other worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet found orbiting a star similar to the Sun, further reinforced the idea that planets are quite common throughout the universe. This gas giant, located about 50 light-years away, marked the beginning of an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri b, discovered in 2016. This exoplanet orbits Proxima Centauri, the closest star to our Sun, at a distance of only 424 light-years. Proxima Centauri b is located in the habitable zone of its star, where all the conditions for the existence of liquid water could occur. This proximity and its potential habitability make this planet a priority target for future exploration and even possible colonization. The discovery of Proxima Centauri b was possible thanks to the radial velocity method, which allows detecting subtle fluctuations in the movement of the star caused by the gravitational attraction of the planet that orbits around it. So far, this method has helped to identify more than 1,000 exoplanets, each of which has become the next step in the search for a world in which life can exist. The viability of interstellar travel depends directly on our ability to develop powerful and efficient propulsion systems. Current space travel technology has made significant advances, but is still far from what is needed to travel beyond our solar system. Ion engines represent one of the most advanced forms of space propulsion currently in use. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ion engines use electricity to ionize a propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating a sustained and very efficient thrust. NASA's Dawn spacecraft, launched in 2007, is a prominent example of the capabilities of ion propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Vesta and the dwarf planet Ceres. Ion propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been prohibitively expensive using conventional rockets. Ion engines have a high specific impulse, which means they use fuel far more efficiently than chemical rockets. This efficiency is critical for long-duration missions, as it allows spacecraft to carry less fuel overall. However, The downside is that ion engines produce much less thrust than chemical rockets, making them unsuitable for launching spacecraft from Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was NASA's New Horizons probe, launched in 2006. The spacecraft was to explore Pluto and its moons, providing humanity with the first images of this distant world at an incredibly close distance. The probe journey did not stop at Pluto, but continued towards the Kuiper Belt, a region full of icy bodies and remnants from the formation of the solar system. New Horizons used a combination of chemical propulsion and gravitational assist to reach its high speed. After launch, the spacecraft received gravitational assistance from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years, an amazing achievement given the enormous distances involved. While New Horizons demonstrates the current level of space travel capabilities, it also highlights its limitations. Despite reaching speeds of more than 36,000 miles per hour, the spacecraft took almost a decade to reach Pluto and even longer to continue its journey to the Kuiper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of reaching much higher speeds for extended periods. Meanwhile, the most intriguing and historically significant advanced propulsion concept is nuclear pulse propulsion. This technology, conceived during the Cold War, consists of using a series of controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislaw Ulam in the 1950s and was subsequently developed into Project Orion. The basic principle of nuclear pulse propulsion is relatively simple. Small nuclear bombs are launched behind the spacecraft and detonated, with the resulting explosions providing a powerful thrust. A large drive plate attached to the spacecraft absorbs the force of the explosion and propels the spacecraft forward. The potential of Project Orion was enormous. Calculations showed that such a spacecraft could reach speeds of up to 10% of light speed, making it one of the fastest propulsion methods ever proposed. Such capability would significantly reduce travel time to nearby star systems, including our neighbor Alpha Centauri. Meanwhile, in recent years, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel within our lifetime. The goal of this international scientific project is to send a probe to Alpha Centauri and, possibly, reach it in just 20 years. The main innovation of Breakthrough Starshot is the use of a light sail propelled by a series of powerful ground-based lasers. This light sail, which is a thin and highly reflective sheet, will accelerate to extremely high speeds by transferring the momentum of millions of laser beams. Unlike traditional propulsion methods, this system does not carry fuel, making it extremely light and, theoretically, capable of reaching speeds of up to 20% of light speed. However, the realization of this technology is not without its challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of current power plants. Synchronizing approximately 100 million lasers to focus their beams on the light sail is a technical obstacle of great magnitude. To solve this problem, researchers at the Australian National University have proposed using a laser guide satellite to help maintain accurate targeting throughout the journey. Despite these challenges, the potential benefits of this technology are enormous. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images of Alpha Centauri, providing an unprecedented view of our closest star system. Music system. While solar sails represent a promising technology for the near future, other cutting-edge concepts are pushing the limits of our understanding of physics. Among them is the theoretical warp drive, inspired by Einstein's general theory of relativity. Einstein's general theory of relativity. A warp engine would manipulate the space-time itself, compressing the space in front of the spacecraft and expanding it behind, which would allow the ship to travel faster than the speed of light without violating the laws of physics. The concept of warp propulsion gained attention after the 1994 publication of an article by physicist Miguel Alcubierre, who proposed a theoretical basis for the engine. Although the concept is currently speculative and requires exotic matter with negative energy density, warp propulsion remains a tempting possibility. Another innovative idea for interstellar travel is Freeman Dyson's interstellar engine. This hypothetical propulsion system would harness a star's energy through a series of mirrors or lenses to concentrate stellar energy on a spacecraft. The collected energy would then be converted into thrust, propelling the ship to high speeds. Although the Dyson concept is intriguing, its practical realization faces serious obstacles. Capturing and converting enough stellar energy to achieve significant thrust would require materials and engineering capabilities far greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is one based on antimatter. Antimatter, upon coming into contact with matter, annihilates both particles and releases enormous energy amounts. A spacecraft propelled by antimatter could, in theory, reach speeds close to a significant fraction of light speed. The potential of antimatter propulsion is amazing, but so are the challenges it poses. The production of antimatter is currently a very inefficient and costly process, and its safe storage presents additional challenges due to its highly reactive nature. Despite these obstacles, research on antimatter continues, as it promises to be an engine of one of the challenges. The production of antimatter is currently a very inefficient and costly process, and its safe storage poses additional challenges due to its highly reactive nature. Despite these obstacles, research on antimatter continues, as it promises to be an engine of unprecedented efficiency. The enormous distances represent the most obvious obstacle. However, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is an enormous undertaking that poses technical and logistical challenges, even with the most advanced propulsion system. Traveling to our nearest star system, Alpha Centauri, requires overcoming enormous technical obstacles. One of the main technical problems is protection against radiation. Space is full of high-energy particles from the sun and distant sources. Prolonged exposure to this radiation can be deadly to both humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect themselves from radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being investigated, including the use of magnetic fields to deflect charged particles and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical obstacle is maintaining the structural integrity of the spacecraft themselves in the long term. Spacecraft designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and potential collisions with micrometeorites and other space debris. The high speeds required for interstellar travel exacerbate these risks, as at such speeds, even the smallest particles can cause significant damage. Engineers are exploring advanced materials, such as carbon composites and reinforced alloys, to improve spacecraft durability. In addition, modular designs that allow in-flight repair and maintenance could be critical for long-duration missions. The vastness of space presents another logistical challenge. Even at a significant fraction of light speed, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft reliably operational for so long. Solutions, such as hibernation or suspended animation, are already being explored, but these technologies are still in the experimental phase. In addition to the technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical, no pun intended. Governments, private companies, and international consortia will have to collaborate and contribute resources. Historically, space exploration has been primarily funded by national governments. But the increasing participation of private companies, such as SpaceX and Blue Origin, suggests a possible shift towards more diversified funding models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy. As you may already know, the discovery of Proxima Centauri b in 2016 was an important milestone that demonstrated the possibility of habitable worlds existing in the star system closest to us. This exoplanet has given rise to numerous research missions and initiatives aimed at determining its characteristics and its potential to harbor life. To continue this research, the European Southern Observatory has developed a new instrument specifically designed to search for exoplanets in the Alpha Centauri system. This advanced instrument, which is part of the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by increasing the precision of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars, focusing on Alpha Centauri A and B, the two stars in the system that are similar to the Sun. This instrument seeks to detect additional planets that may be located within their habitable zones. The greater sensitivity and resolution of this technology promise to reveal planets that have not been detected previously, giving us a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be underestimated. Such a discovery would be a huge step forward in our quest to understand how widespread habitable conditions are beyond our solar system. Such a habitable planet would be an ideal candidate for future interstellar missions and a potential target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, in late spring this year, astronomers discovered the Earth-like exoplanet Gliese 12b, located just 40 light-years away. This planet, similar in size to Venus, orbits a red dwarf star, and scientists estimate it has a surface temperature of about 42 degrees Celsius. The discovery of this type of planet, which could have an atmosphere, provides information about the conditions necessary for a planet to conserve an atmosphere and for liquid water to exist. The discovery was possible thanks to NASA's Satellite for Exoplanet Transit surveys, which detects exoplanets by observing a slight dimming of a star when the planet passes in front. During these transits, the light of the star crosses the atmosphere of the exoplanet atmosphere of the planet, which allows astronomers to analyze its composition by means of transmission spectroscopy. The importance of Gliese 12b goes beyond its potential habitability, as it serves as a valuable point of comparison to understand why Earth and Venus, despite their similarities, have such different environments. By studying Gliese 12b, scientists hope to learn more about atmospheric retention and the evolutionary paths of Earth-like planets that orbit cold stars, which are the most common type of star in the Milky Way. The estimated size of Gliese 12b may be as large as Earth or slightly smaller, comparable to Venus in our solar system. The efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as the JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one suggests that humans should be the first to explore these distant worlds, even without the advanced technology necessary for human survival. We can still send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role in the future exploration of interstellar space. These technologies can operate autonomously, performing complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is that of von Neumann probes. These theoretical self-replicating machines could explore the galaxy using local materials to create replicas, thus increasing the number of probes with each replication. This approach could allow exhaustive exploration and possible colonization without the need for constant resupply from Earth. However, When it comes to human space exploration, the idea of interstellar arcs and self-sustaining habitats represents a visionary approach to colonizing distant star systems. These enormous spaceships would house large communities and provide everything necessary to sustain life during multi-generational trips to other stars. These habitats would be equipped with advanced life support systems, agricultural facilities, and social infrastructure to guarantee the well-being of their inhabitants. In conclusion, although our current technology limits us to relatively modest space trips, these advanced concepts allow us to glimpse a future in which we can transcend the spatial barriers that confine us to our solar system. As technology advances, these concepts could move from science fiction to reality, paving humanity's way to the stars. Music, imagine a line, a simple, uninterrupted line that extends to infinity. This line, in its purest form, represents the first dimension, a realm of length, but without depth, an infinitely long but impossibly thin universe. Now let's expand our perspective. Let's introduce a second line that intersects the first and suddenly, in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable foreign to them. By taking one more step, we find ourselves in the familiar embrace of the third dimension. This is where depth comes into play, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe acquires texture and form. But what if we go out to another layer? Time is the elusive fourth dimension that permeates our three-dimensional space, invisible but omnipresent, that dictates the rhythm of our lives, a continuous thread that connects each previous moment with the current one and the current one with the next. In this realm, our understanding of reality becomes broader and more complex. Here, the very fabric of the universe reveals its complexity. In dimensions beyond our sensory perception, however, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces governing the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us today in our attempt to unravel their mysteries together, one dimension after another, in a historical context. The concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. The philosophers of yesteryear reflected on the nature of existence, laying the foundations for our understanding of space. In their debates, they questioned the very essence of reality, imagining realms beyond the tangible. Over the centuries, these philosophical speculations paved the way for a more structured investigation into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions forming the fabric of space-time. Albert Einstein, in turn, based on the foundations established by Minkowski, presented the revolutionary theory of general relativity, which restructured our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical search of ancient thinkers to the scientific revolutions unleashed by Minkowski and Einstein, the journey through the evolution of spatial thought reveals an incessant search to understand the true nature of our universe. Thus, over time, we have come to understand that to truly understand the structure of our reality, we must go beyond the three tangible dimensions and enter the realm of the fourth dimension, time. The concept of time as a dimension is profound and compelling, as it defines our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It advances inexorably from the past, through the present, and toward the future. This unidirectional flow of time distinguishes it from space and contributes to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, let's consider a simple, everyday scenario: organizing a meeting. When we suggest to someone to meet in a certain place, we unconsciously navigate the three basic spatial dimensions to determine where it makes sense for us to meet. If we were to arrive at different places, the meeting would not take place. However, the dimension without which the meeting could not occur is no less important. If you and your friend arrive at the same place, but at different times, we will not be able to see each other. This entanglement of space and time is manifest in the concept of a world line, the path an object or person travels through space-time, representing its history and future. The idea of world lines offers a vivid illustration of how events link together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not only a spatial coordinate, but a space-time coordinate. It's the only point in the vast continuum of the universe in which place and time coincide. This principle applies not only to simple encounters, but also to the fundamental functioning of the cosmos. Celestial bodies, from planets to stars, trace their world lines through space-time, their trajectories determined by the interaction of spatial positions and temporal moments. For example, the orbit of the Earth around the Sun is not only a trajectory through space, but a continuous journey through time, in which each point of the orbit represents a unique moment. The integration of time as a dimension profoundly affects our perception of the universe. It forces us to look beyond the static images of space towards the dynamic unfolding of events. Time allows us to understand the universe not as individual moments, but as a continuous narrative in which cause and effect unite our reality into a coherent whole. The inclusion of time as a dimension has catalyzed important advances in physics, particularly through Einstein's theories of relativity, which we have already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, that it slows down or contracts depending on the speed of an object, challenges the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different frames of reference. This phenomenon is confirmed by experiments, for example, with atomic clocks on airplanes moving at high speed. In quantum mechanics, time as a dimension underlies the evolution of the state of particles, governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, in which the temporal dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens a door to a realm where our everyday experience and the laws of physics, as we know them, are fundamentally questioned and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the structure of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not only speculative constructions, but important components in the search for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to some of the most challenging mysteries of physics, such as the unification of fundamental forces and the nature of gravity on a quantum scale. The difficulty in visualizing higher dimensions lies in the fact that our perception is inherently three-dimensional, so analogies become an invaluable tool. One of the classic analogies to help understand higher dimensions is to imagine the perspective of a two-dimensional being, often called a planter, who lives in a flat, two-dimensional world. This being can move forward and backward, left and right, but has no concept of up and down movement, as these dimensions do not exist in its two-dimensional experience. Let's imagine a three-dimensional sphere passing through this two-dimensional world. For a planter, the sphere would first appear as a point when it was touching the two-dimensional plane and would gradually turn into a circle as more parts of the sphere pass through the plane, and then shrinks again to become a point when the sphere leaves the plane before disappearing completely. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, postulates that particles are not the individual points we see, but small vibrating strings whose modes of vibration determine their properties. This theory requires the existence of more than the 4 known dimensions. In fact, it suggests that there may be up to 10 or 11. These additional dimensions are compacted or convoluted, so they are imperceptible to our scale. Like the sphere in the example of the plane in the 5th dimension, we find a space that contains all possible universes that start from the same initial conditions as our own universe. Let's imagine a tree in which each branch represents a different decision or outcome that leads to a different reality, all of them coming from the same trunk. Just as a person who is at the foot of the tree can choose which branch to climb, a being with access to the 5th dimension can explore these alternative realities, each of them a variation of our own universe, but with slightly different results. The ascent to the 6th dimension opens a plane that contains all possible universes with the same initial conditions as ours, but with any possible set of physical laws. If we think of each universe as a sheet of paper, the 6th dimension would be like a stack of sheets, each representing a different universe. A being capable of traveling through the 6th dimension could jump between these universes, learning the different outcomes and laws that govern each reality. The 7th dimension expands this concept to include universes that start from different initial conditions. Using an analogy with a library, each book represents a different universe. The 7th dimension encompasses the entire library, offering not only different stories, universes with the same initial conditions as ours, but with different results, but also universes with completely different initial conditions. A 7-dimensional being could move through this library experiencing an infinite number of universes, each with its own initial conditions and physical laws. In the 8th dimension, we find a network of all possible universes, each with its own initial conditions and physical laws, as well as all possible variants of its development over time. Imagine a huge network in which each thread represents the timeline of an independent universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire network, allowing us to trace journeys between any node and explore the connections between different universes and their histories. As we approach the 9th dimension, we encounter all possible physical laws and initial conditions that have ever existed or will ever exist. This dimension can be compared to the art of origami, where a single sheet of paper can be folded into numerous shapes, each fold representing a change in the initial conditions or the laws of the universe. And the 9th dimension includes all possible combinations, resulting in all conceivable and inconceivable universes. A being living in the 9th dimension will not only have absolute freedom to cross the boundaries between all possible realms of reality, but will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It is the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network in which each branch represents a different outcome or timeline, and all branches eventually converge at one point, the 10th dimension. Visualizing the 10th dimension poses a challenge due to its abstract nature. One approach involves using the analogy of a tree where each branch represents a temporal line or different universe, and each leaf represents a possible outcome within that universe. When moving from the trunk to the leaves, we transition from the initial conditions of the universe, the lower dimensions, through the diverse choices and events, the higher dimensions, that lead to all the possible outcomes. The 10th dimension represents the point at which all these possibilities converge, the singularity of infinite potential outcomes. This suggests a cosmos where all the possible outcomes not only can occur, but do occur in some temporal line or universe in the 10th dimension. The concept itself invites us to reflect on the immensity of possibilities that lie beyond our observable universe. It raises questions about destiny, choice, and the underlying structure of the cosmos, leading to a broader exploration of the potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and time in four dimensions has profound implications for both physics and cosmology. This field of study is designed not only to challenge our fundamental understanding of the universe, but may also hold the key to uniting the disparate forces of nature, potentially resolving some of cosmology's most enigmatic puzzles. The recognition of the existence of higher dimensions plays a key role in the search for a theory of everything, a unique framework that perfectly unifies general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. The higher dimensions may also offer new perspectives on cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter could be gravitational effects from matter in parallel universes, a concept of M-theory that suggests the existence of multiple membranes or parallel universes as fundamental components of the universe, each of which could contain another universe in higher dimensions. Looking to the future, in the field of energy, mastering the complexities of the higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot even imagine now and lead to the creation of clean and practically inexhaustible energy sources. Similarly, the field of space travel could be revolutionized with a better understanding of the structure of space-time, which might ultimately allow warp drives or other forms of faster-than-light travel. These are concepts that currently belong to the realm of science fiction, but that could be theoretically plausible in higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle accelerators, such as the Large Hadron Collider at CERN, in search of evidence of additional dimensions and of the particles that might inhabit them. This experimental work is complemented by theoretical studies that immerse physicists and mathematicians in the abstract realms of high-dimensional spaces. Upon completing our journey through the dimensions, from the simplicity of a line that extends to infinity to the unfathomable complexity of the 10th dimension, we face the inherent challenge of visualizing spaces beyond our three-dimensional experience. We face the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through mathematics, we can describe properties and relations within higher dimensions, and physics offers theories, such as string theory and M-theory, that point to the existence of these additional dimensions. Animations such as Tay-Sachs allow us to conceptualize high-dimensional forms and their projections or shadows in lower dimensions. A deeper exploration of the higher dimensions promises to evolve our understanding of the universe, just as the transition from flat Earth to a spherical one centuries ago broadened the horizons of humanity. This expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place within it.